Assalamu alaikum wa rahmatullah. This is Dr. Muhammad Saad, and we are continuing our lectures on computer communications and networks. And we are still in the introduction chapter, and we are still talking about the idea of the layers. In the previous video, we talked about the general definition of the layers, the idea that network functionalities are divided into layers, abstract layers that define different network functionalities. These layers are designed in such a way so that each layer provides a service to the layer on top, which means eventually all these layers are helping the layer on top, which is the application layer, gets its message delivered. We talked about a hypothetical general example in the previous video, which basically clarifies the idea of encapsulation, adding headers at the sender side, and decapsulation, removing headers at the receiver side. Each one of these headers contains extra control information additional to the actual data, extra control information which contains information which is not part of the data, however still essential, needed to get this message delivered, like address information, like sequence number information, error control information, and so on. And however, today in this video, we would like to talk about the actual layers that exist and what these layers are doing. So our first reference model that we are covering is called the Open Systems Interconnection Reference Model, the OSI reference model, which has 7 layers. Again, OSI stands for Open System Interconnection, and this model of layers was developed by the ISO organization, the International Standards Organization. So this is an organization that deals with standards. Basically, they sat down together and they said, okay, network people, network designers, if you want to deal with layers, this is what we recommend. This is what we suggest. It's a system that has 7 layers. And this is what we would like to talk about now. And then after we finish this, we have a second reference model, which is called the TCP/IP reference model, or the Internet reference model. It did not come from ISO, however, it came as a de facto system of layers, a de facto set of layers that came from the implementation of the Internet. We are covering both. They have large similarities, and we start with the Open System Interconnection reference model, the OSI reference model that was developed by ISO. So this reference model has 7 layers. As you notice, layer 1, 2, 3, 4, 5, 6, and 7. Before we go to the details of the layers, please notice the figure as a whole. How many devices, how many computers here do we have in this figure? So this figure represents host A here. On the left, we have host A that communicates with host B. So these are 2 hosts, like me sitting on my laptop and you sitting on your phone, for example, or your desktop, and I'm sending you a message. Connecting us are 2 routers, router A and router B, or router 1 and router 2. To be more specific, I added this illustration here. So these layers here correspond to 4 devices, host A communicating with host B, and these 2 hosts are interconnected by subnet, the core of the network, which has a router and a second router. So the first thing that you notice here is that the host, which is the user device, like our desktops and laptops, the user hosts have 7 layers, while the routers in the middle of the network have only 3 layers. Remember the meaning of the layers? The layers basically is a grouping of network functionalities, right? The end hosts have more functionalities. Let me give you a certificate. What about the application layer? What did it indicate? The application layer corresponds to those protocols done by the application itself. What are routers? Routers in the middle of the network. Routers are switching devices. So the job of a router is to receive a message and then look at the header, decide what is the best outgoing link for this message, and then send it to the next router, and so on. So in a very simple way, it is very easy, it is very intuitive to imagine that routers don't need an application layer. They don't have applications. They don't have web browsers. Routers don't use web browsers. They don't use email software. All these applications are not used by the routers. To be more specific, these top 4 layers are not needed by the routers. It is only the bottom 3. And this is just a note here. However, we are continuing with the details. So what are these 7 layers? The first layer is called the physical layer. Layer 2 is called data link layer. Layer 3 is called the network layer, transport layer, session layer, presentation layer, and application layer on top. So the bottom layer 1 is called the physical layer, and the top layer number 7 is called the application layer. As we have just mentioned, the routers have only the bottom 3: physical, data link, and network layer. What are these layers doing? Pretty much on each slide we have a simple description of each one of these layers, what they are doing. However, let me summarize here. So what is the job of the physical layer? As the name suggests, it's responsible for the physical transmission of the bit sequence. The message at the end of the day corresponds to a binary sequence, ones and zeros. The physical layer's job is to get these ones and zeros transmitted. So what is the main job of the physical layer? At the sender side, transmission of these ones and zeros, and at the receiver side, receiving these ones and zeros and recognizing them correctly. So the physical layer's main task is to make sure that 1 is received as 1 and not a 0, and the 0 is received as a 0. So what are the details of the physical layer? What is the physical layer doing? It is pretty much doing what you would study in telecom. So in a telecommunications course like Telecom 1 and Telecom 2, you would study what we have in a physical layer, what the physical layer is doing. And this would involve modulation techniques, demodulation, detection, line coding. Line coding means deciding on the waveforms. What is the signal waveform that corresponds to a 1, and what is the signal waveform that corresponds to a 0? How are these bits detected, and so on? And how are they transmitted physically? This is the physical layer. In this course, we don't focus on the physical layer too much. That's why after we finish our introduction chapter, our next chapter will be on the data link layer. And the chapters of our textbook are pretty much following the layers. So here we have an introduction which represents a big picture, general definitions, and the main idea of the course. And in the future chapters, we will talk about specific layers. Now, let's go to the data link layer. Layer 2 is called the data link layer. The job of the data link layer is the transmission of a frame. Do you still remember the frame? The frame is a group of bits. It's a bit sequence which has some header and a trailer at the end, and then data in the middle. So the main job of the data link layer is the transmission of the frame. And it's a good chance to comment also on these names at the end. So these names represent the names of the data unit handled by each one of the layers. Didn't we say the physical layer is responsible for sending and receiving bits? Raw bit transmission, ones and zeros, right? So the physical layer does not care about the details of these bits. Are they part of the header? Are they part of data? Which header are they part of? They don't care. So the physical layer just deals with the bits. The data link layer deals with the frame. So the main job of the data link layer is to make sure that the frame can be transmitted over a single link. So from device to the next, right? So the data link layer's job is the transmission of the frame from the sending host to the router, and then the transmission of the frame from the router to the next router, the transmission of the frame from the last router to the receiving host, and so on. So again, the data link layer job is to make sure a frame is transmitted successfully over a single link, from hub to hub over a single link. What does this entail? What does this contain? It contains jobs like error detection and correction, right? So if we have an error, it needs to be detected. So if the transmission here from the sending host to the router, we get some transmission error, some bits arrive incorrectly, it is the data link layer of this router that checks for these errors and then handles this, either asking for retransmission if we're just doing error detection, or even correcting the error so that we generate the correct frame. Another job of the data link layer is framing itself. How does the data link layer deal with frames instead of simply a bit sequence? Because the job of the data link layer at the sender side is to mark the beginning and end of the frame. And we will study this in the next chapter. The beginning and end of the frame are marked so that these marks are recognized by the receiving machine, so that when the receiving machine receives a long bit sequence, It will be able to recognize, okay, this is the beginning of the frame and this is the end of the frame, and then comes the beginning of the next frame and the end of the second frame, and then we have the beginning of the third frame and the end of the third frame. So this marking of the beginning and the end of the frame so that it is recognized by the receiving machine is called framing. So the main two tasks of the data link layer is framing and error control. And what is the net result? The net result is that the data link layer is able to communicate frames error-free. Some other jobs of the data link layer include flow control. Flow control is kind of a speed control. Flow control means the basically controlling how fast a machine is sending so that it does not overwhelm the receiver. How fast is this host sending so that the router is not overwhelmed? And how fast is the router sending so that the next router is overwhelmed, and so on. This is the job of the data link layer, and it is called flow control. Now, if we have a broadcast network, in the previous lectures we talked about broadcast and point-to-point networks. A broadcast network has a single communication channel, like a bus topology or a ring topology or a wireless LAN. We have a communication channel, we have a single communication channel which is shared by all devices or all machines connected to the network. For these kinds of broadcast network, part of the data link layer, so if you think of these layers, part of this layer, a sub-layer of the data link layer, is called the medium access control sub-layer, in short MAC. Again, MAC is a very famous term in networking because there is something called the MAC address. Let's wait until we get to that later. The main job of the medium access control sublayer, which is part of the data link layer, in case we have a broadcast network, is to deal with the problem of multiple access. Do you still remember in a broadcast network, if you have a common communication channel, like if you have a common cable and all machines are connected to this cable, what is the main problem? As in the first and second video, what is the main problem? The main problem, if two machines send at the same time, we get a collision, right? To avoid these collisions, we need to organize transmissions. Who gets to transmit when? Who gets to use the channel when? And we call this the multiple access problem. And the layer responsible for solving this multiple access problem is called medium access control, or MAC sublayer, which is part of the data link layer. Now, we go to layer 3, which is called the network layer, and it deals with a packet. Okay, what is the main job of the network layer? The main job of the network layer is to do routing. Routing means finding the best path for a packet to go as to arrive at the destination efficiently and successfully. So it performs routing as to provide basically a path for the different packets. Of course, routing can be done in different ways. Static routing, in which those routes or paths don't change, or dynamic routing. And again, this is one of the topics in a future chapter. It's a big topic in networking, routing. So you can think of routing as the most important job of the network layer, coming up with a path from source to destination, because typically we have many possible paths from source to destination in a large network. So the network layer's job is to find the best route for every packet. The second job of the network layer is congestion control, making sure that these individual network links don't get congested. If too many packets are traveling through this link, maybe future packets need to go through other links. At least we have to deal with this congestion, detect it, and telling the senders about it so that the senders can slow down transmission, right? So this is the main job of the network layer, routing and congestion control. Going back to broadcast networks. In broadcast networks, usually we have only one possible route, or maybe two. In a ring network, if we have a ring interconnectivity, and then we have two devices on the ring, how can we reach from device 1 to device 2? Maybe going right on the ring or going left on the ring. So we have only two routes instead of many possible routes, as in a mesh topology. And in a bus topology, in a linear network that follows a bus topology, that has a bus topology, there is only one path from device A to device B. There is only one path So basically, in this case, routing does not exist, right? In a bus topology, routing does not exist. In ring topology, routing is simple because we have only two possible routes between any source and any destination. So in general, we can say that in broadcast networks, the network layer is often thin or non-existing. So it's really simple or non-existing because the main task routing is not really a big issue in broadcast networks. Now going back to our protocol, to our reference model here, layer 4 is called the transport layer. And as you notice, the transport layer is the first layer which exists only on the end hosts. We don't have a transport layer in the routers. So the router has a physical data link and network layer. So the job of the router ends with the network layer, which does the routing, guiding the packet along a path until it arrives at the destination. The transport layer is a true end-to-end layer. It exists only on our end host machines like our desktops and laptops, etc. What is the main job of the transport layer? So we say the transport layer's job, first of all, is to break a large message into smaller packets at the transmitter side and assembling the packets back into the original messages at the receiver side, dealing with out of order delivery. So since we have those smaller packets, it is possible that these packets don't arrive in the same order at the destination. So at the destination side, we may be receiving packet 1 and then 2 and then 4 and then 3 and then 6 and then 5 and so on. So dealing with this out of order delivery, basically reordering the packets, is part of the transport layer, and handling the problem of lost packets is also done at the transport layer. In addition to this, the transport layer is doing also end-to-end tasks like end-to-end flow control and congestion control. End-to-end flow control, imagine here we have a sending host sending to a receiving host, but that transmission goes from router to router until we get to the receiving host. If the transmission of the sending host is too fast for the receiving host, so that receiving host cannot handle this fast transmission through the transport layer, it is possible to give this information that you are too fast, to give this information or feedback to the sending host so that it slows down. So this is called flow control. As you have noticed, flow control is done by the network layer and again by the transport layer. What is the difference between them though? The difference is really simple. What was the scope of the data link layer? Sorry, I think we made a mistake. We said a typo. So the flow control is done by the data link layer, and also again by the transport layer. So what is the difference between these two issues here? The difference is really simple. So if the scope is only a single link transmission, so for the transmission from this host to the next router, for that transmission over this link, if the transmission is too fast for the router, slowing down and basically doing flow control in general, slowing down in case we are too fast. Since we're talking about one link transmission, one hop transmission, this is the job of the data link layer. Slowing down end to end, so regardless of what happens inside of the network or in the core of the network, host 2, host B, asking host A to slow down because the transmission is too fast for the host itself, regardless of the routers. This is done by the transport layer. So that's why we say end-to-end flow control, end-to-end congestion control is also possible. So basically, hosts need to slow down when the network gets congested, and this job is really divided by the network layer and the transport layer. We mentioned this at the network layer here, congestion control. We mentioned that at the network layer, and we will come to this in this course. Basically, routers monitor if the links are congested or not, and if the links become congested, the routers provide feedback to the senders to slow down. So this job done by the router of observing how the link is occupied, how the link is used, whether it's congested or not, and providing this feedback to the sending host, this is done by the network layer. What happens at the end host itself, the act of slowing down, how much does it slow down, when does it speed up again, and all these details, this is part of the transport layer. To summarize things, the main job of the transport layer includes end-to-end flow control and congestion control. It may even perform end-to-end error controls. When the packet arrives at the final destination and the final destination detects some errors, dealing with these errors, either by detection or correction, is done by the transport layer. So as you notice, the transport layer is doing end-to-end tasks between the end hosts. Now, on top of the transport layer, we have the session layer. According to the OSI, the Open Systems Interconnection Model, which was developed by ISO, the idea was that the session layer is responsible for establishing communication sessions, establishing connections, right? Establishing a connection between host A and host B. This is the job of the session layer. Allow users on different machines to establish communication sessions or connections between them. Now, the second to last layer, layer 6, is called the presentation layer. And the job of the presentation layer is not related to communications, but it's related to the data. It's related to the format of the data, or in other words, syntax and semantics of the information transmitted. So what does the presentation layer do at the end of the day? It may perform tasks like encryption. If you would like to change how the data looks like so that people can't understand except the end host that would have the decryption key so that the data goes back into its original format. So this is part of security. If you take a security course, you would study this more. But in case we are having a secure connection and we need to do encryption, this is done by the presentation layer, originally suggested to be done by the presentation layer. If we need to do data compression means putting the data in smaller size, compressing the data. Instead of using 1,000 bits, no, compressing it into only 700 bits, let's say, without losing data. We have techniques for data compression in case this is done. It is also done by the presentation layer. Finally, file format transfer. Imagine the sender is sending a video using a format like MP4, but the receiver does not understand this format. So what can we do? How can we convert between different file formats? So this is also the job of the presentation layer. And now finally we have layer 7, which is called the application layer. All protocols related to the application itself, whether the application is a web browsing application, or an email application, or a video like a YouTube, or streaming a multimedia application like video conferencing or Skype, or these kinds of real-time applications. So everything related to the application is part of the application layer. So that's it. This is basically what we call the OSI Open Systems Interconnection Reference Model, the 7 layers: physical, data link, network, transport, session, presentation, and the application layer. Before we go to the next reference model, the TCP/IP reference model, let me remind you of the names of the data units understood by the different layers. So again, the bit, just the bit, the 1 or the 0, this is basically handled by the physical layer. The data link layer handles the frame, right? The frame is a number of bits that starts with a header and usually ends with a trailer containing extra control information. The network layer deals with the packet. Now, before we continue going up, what is the relation between the packet and the frame? If the data is generated at the sender side here, the data comes from the application and then it goes down the layers. What were the layers doing? The layers were adding headers, right? So the presentation layer will add a header, the session layer will add a header. It does the same thing as we have said here in this hypothetical example. So layers are adding headers, which is called encapsulation at the sender side, and these headers are removed at the receiver side, which is called decapsulation. Having said that, what is the relation between the packet and the frame? The frame is just the packet itself in addition to an extra header and trailer at the end. So the frame, you can think of the frame as an envelope which contains the packet, an envelope which contains the packet. So the frame contains the packet itself in addition to an extra header and trailer, right? Okay, what about these other names? TPDU, SPDU, PPDU, and APDU. You notice that the letters PDU are common, protocol data unit. So PDU stands for protocol data unit, and that T is the name of the layer, so transport protocol data unit. Again, these abbreviations are nothing fancy. We just want to say that TPDU is the name of the data unit handled by the transport layer. Simply transport protocol data unit, session protocol data unit, presentation protocol data unit, and application protocol data unit. So basically, this is about it, just the names of the data units understood and handled by each one of these layers. Of course, we have the protocols as well. So the protocol, again, is the set of rules that governs the exchange of information. We always have a protocol so that transport can talk with transport, network can talk with network, and so on. And it is time to go to the next reference model, and we call it the TCP/IP, or the Internet Reference Model. TCP and IP happen to be basically the most two famous protocols in the Internet. The IP protocol, it's called the Internet Protocol, and the Transmission Control Protocol. These are the most two famous, basically the two legs on top of which the Internet stands. So that's why this reference model is named after them, TCP/IP reference model. This is our OSI, Open Systems Interconnection, that was suggested or recommended by ISO, which has the 7 layers. Now TCP/IP has only 4 layers, so this Internet Reference Model has 4 layers, 1, 2, 3, 4. But there is still an analogy between the 7 layers and the TCP/IP 4 layers. So the link layer that comes in the bottom here, the link layer is basically equivalent to physical and data link layer of the OSI reference model. Internet layer is the same as the network layer. Transport is the same as transport. Application is the same as application. So session and presentation are not available simply because the tasks that were originally intended for session and presentation layer are done by the other layers. So that's why these two layers are not available. So again, we have a one-to-one correspondence between these layers. So link is equivalent to physical and data link, internet, network, transport, application. However, still we have some extra details that we can cover, and that's why pretty much we have, for each one of these layers, we have a slide that talks about the layer. Now, if we start with the link layer, the link layer is basically equivalent to physical and data link layer, so the transmission, the physical transmission of the ones and the zeros, and in addition to basically sending frames over a single link in the network, so from machine to the next. This is the job of the link layer, which includes physical transmission of ones and zeros, in addition to the data link layer techniques such as framing, marking the beginning and the end of the frame so that it's recognized by the receiving machine, and the error control and flow control. So this is the job of the link layer, equivalent to physical and data link. Let's leave it this way. Now, the internet layer is the same as the network layer. When we talked about the network layer in the Open Systems Interconnection reference model, what did we say? We said that the main task of the network layer is to do routing and congestion control. Routing, guiding the packet from the sending host, going through routers from router to router until it arrives at the destination or the receiving host, such that the packet goes through a good route, through the best possible route or the best possible path, right? And this is the same for the internet layer. So in the TCP/IP model, the internet layer's main job is routing and congestion control as well, avoiding network congestion. In addition to this, we have some extra details. The fact that in the TCP/IP reference model, that internet layer or the network layer is always connectionless, because in general we said layers could be connectionless or connection oriented. In connection oriented, we have to establish a connection first, and then we send our messages, and then we release the connection. In connectionless, we don't have it. Messages are broken into smaller packets. Each packet has a header which contains full address of the source and full address of the destination. This is the connectionless service, and here in the internet layer of the TCP/IP reference model, it has been decided that this layer, the internet layer, is always connectionless. Regarding the details of the internet layer, what does it define exactly? It defines the packet format, the format of the packet. You know, the packet has data in addition to a header. That header, so far, we have been saying that this header contains control information, extra control information, such as sequence numbers, addresses, and so on. So how is this header basically, how are the bits of the header organized? What is the format of the header? What is the use of the first 4 bits of the header and then the next 8 bits of the header and so on. This is what we mean by the packet format, and this packet format is part of the internet layer. There is a specific packet format that is basically agreed upon, and all network users, all machines sending and receiving messages or packets in a network are using the same packet format, and we will study that later as well. So in addition to agreeing on a specific packet format, the internet layer also is using a famous protocol called the Internet Protocol, the IP protocol, which includes all the details of what the internet layer is doing in particular, and we will come to this later as well. So going back to this picture here, so the internet layer is equivalent to the network layer with some additional details. We said that the internet layer is connectionless. It defines a packet format and it uses the internet protocol, the IP protocol. Transport layer is equivalent to transport. What was the main job of the transport layer when we talked about it in OSI? The main job is to break larger messages into smaller packets, dealing with out of order delivery and packet losses, right? Doing end-to-end flow control, end-to-end error control, end-to-end congestion control. That's exactly what we say here as well. This is the job of the transport layer in the TCP/IP model as well. In addition to this, we can mention to you that at the transport layer, we have two main protocols that we can choose from. Two main protocols that can be used depending on what is the application that is using the network. One of the protocols is called TCP, the Transport Control Protocol, or the Transmission Control Protocol. The other one is called the UDP, User Datagram Protocol. By the way, this discipline of networking, and it's even written in books, it uses basically a lot of abbreviations. It uses a lot of abbreviations, so that's just the style of this discipline. It is not me, it is not this course, it is just this networking disciplines, but we try to clarify everything as much as possible. Okay, so TCP versus UDP. These are the two main protocols that we can choose from at the transport layer. What is the main difference between them? So when we talk about TCP, it is really a reliable connection-oriented protocol. It's a reliable connection-oriented protocol. Reliable in the sense that if we send our messages and something gets lost, we have to resend. We have to make sure that every transmitted message or every transmitted packet arrives at the destination, and we cannot tolerate any losses. And this is what we call reliable. So if we are using TCP, if we are using the TCP protocol at the transport layer, it means everything needs to be delivered. If a packet gets lost, it will be retransmitted. We have a reliable protocol. Connection oriented means that here, if I go back to this picture, this sending host has a number of packets that needs to be sent to the receiving host. Before sending the packets, the transport layer on host A will get in contact with the transport layer of host B by exchanging some control messages as to establish an explicit connection between them. So before sending the actual data messages or data packets, host A will ask host B, can we establish a connection? Host B will acknowledge this, and this is done in some steps, and this is done before host A can start sending any data message or any data packet. And as long as this happens, we have a connection-oriented protocol, and TCP, as I'm trying to explain here, is a connection-oriented protocol, right? Once the connection has been established between the end hosts, our packets are sent one by one to go from sender to receiver. Now, UDP, User Datagram Protocol, the User Datagram Protocol is exactly the opposite. It's an unreliable, connectionless protocol. Unreliable in the sense that if packets get lost, we will not do anything. We just tolerate losses and we don't resend them or anything. It is connectionless in the sense that we don't have this agreement to establish a connection. If the sender has something to send, it will just send without establishing a connection first. Now, what you may ask me here is that as long as we have TCP, which sounds nice and good and efficient, reliable. We cannot, if something gets lost, we have to make sure that we deliver it by resending, and it's connection oriented. We don't send unless we establish a connection. Then why do we have this other protocol called UDP? Simply because applications are not all the same. Network applications have different requirements. So imagine if we have a web browsing application. So you go to your browser and then you type cnn.com. What happens is that your computer will send a request to the CNN server, basically to get some content sent from that CNN server to your machine. Basically, you want to see the website. In this kind of application, we cannot tolerate any losses. If you want to see a website, you are expecting to see all information without losses, right? So for this kind of application, TCP is suitable. However, for some other applications, UDP is suitable simply because in some other applications we can tolerate losses. Losses would not cause a big problem, like in some multimedia applications, especially real-time multimedia applications, like streaming multimedia applications, like video conferencing, when we're talking over the internet, having a phone call over the internet, like if we're having a chat using Skype, using voice and video, for instance. These kinds of applications like Skype and so on, these kinds of applications are better using UDP, the user datagram protocol, because if a packet gets lost, if a packet among thousands of packets gets lost, maybe the end user would not notice a big difference. However, what matters the most is the delay. So for these kinds of applications, we want to make sure that packets are delivered as fast as possible. Otherwise, the quality will degrade. So for those applications that basically in which prompt delivery, fast delivery is more important than accurate delivery, like if we're having losses or so, if we don't care about the losses too much, for these applications, UDP is the suitable protocol. Again, if we go back to the transport layer, the transport layer is similar to the transport layer in the Open Systems Interconnection OSI reference model, but we added here some information that at the transport layer, typically we have the most two famous protocols that we can choose, that our application can choose from, which is TCP and UDP. Now, the application layer is the same as the application layer, but let's mention some example protocols that are really part of the application layer. So we have a protocol called the FTP, the File Transfer Protocol. It's for sending and receiving files between remote machines. So I can write and read a file from my machine to another remote machine over a network. FTP, the File Transfer Protocol, it's an application layer protocol. Email applications use protocols, something like SMTP, the Simple Mail Transfer Protocol, like the details of how email messages are sent and received. So this is also an application layer protocol. In the internet, we have something very important called DNS, Domain Name System. Domain Name System means translating a network name into a network address. A network name like cnn.com or sharjah.ac.ae or mit.edu. These are network names. These are network names or host names. To actually send messages or packets to these hosts or to these machines, we have to use a network address which consists of numbers. Later on in the course, we will call them IP addresses. How can we translate a network name like cnn.com into its corresponding address which consists of numbers? We have an application called DNS, Domain Name System, and DNS here is nothing but a protocol which works at the application layer. HTTP, the Hypertext Transfer Protocol, it's a protocol for displaying websites. So whenever you write cnn.com or any website, sharjah.ac.ae or mit.edu, or if you want to display any website, we are using an HTTP protocol which displays the information of the website. So these are some example application layer protocols. We started with the link layer protocol at the very beginning, and we said that the link layer pretty much is corresponding to the physical and data link layer. Now, I will stop here and finish the chapter in the next video, inshallah. Assalamu alaikum wa rahmatullah.